Hi everyone. Today we're going to be practicing solving some heating and cooling curve calculations. So the worksheet that I'm using is 9.4b, version B. So the version you had for homework was version A. We're going to be working through version B. So the things that we want to keep in mind, there's two different equations that we could potentially use to calculate energy. The one that we see on the left is going to be for temperature changes, and the one that we see on the right is going to be for phase changes. So if we look at a heating curve, let's just say a quick heating curve that I'm kind of drawing over top of this, the portions that we would see using this equation would be those slanted areas of the graph. When we would see the phase change equation being used, that's what we would see in these straight portions of the graph. So what we want to do is read our problem, decide what portion of the graph it's going to occur on, and then decide what equation to use. So if we look at this first problem, we read through it. Calculate the amount of heat that must be absorbed to increase the temperature of 15.3 grams of water from 12 degrees to 58 degrees. What you see there indicates that you have a temperature change. You are provided with an initial and a final temperature. That's your hint that this is going to be a temperature change problem, meaning the equation that we use is m times delta T, change in temperature, times C. So I want to draw a heating curve really quickly because I'm going to need to decide what value of C to use. So we're going to go through and figure out our variables in a second. So in a typical heating curve for water, it's what it looks like. 0 degrees and 100 degrees are at those two intersections. So that's the melting and the boiling point of water. So if we're going from 12 degrees to 58 degrees, we're going to be in this region of the graph. So that's going to be that range 12 to 58 degrees. So that region there. So this is going to be a liquid. So I just want to keep that in mind. My mass is 15.3 grams. My change in temperature, so we end at 58. We started at 12. The difference there that we see is 46. And the specific heat that I want to use, I want to choose the specific heat of liquid water, which is going to be 1 calorie per gram degrees Celsius. So when I plug all that into my equation, 15.3 times 46 times 1.0, the answer that I get is 703.8 calories. In correct significant figures, that's 704 calories. So the reason why we wanted to use this equation again is because we had that temperature change there. So if you see that you are provided with two temperatures, that's your hint that you're at least going to need a temperature change equation. And if we look at this graph that I drew, it's another reason why the graphs are really helpful to draw ahead of time. We can see that we're only in a tiny portion of this curve, so we don't have to worry about using more than one equation. We're not changing state at all. All we're doing here is just changing temperature. So let's try the next one. Calculate the amount of heat needed to turn 10.8 grams of liquid water into steam at 100 degrees. So your key word here, when you're reading through these problems, if you see the word turn or change or any of those state change terms that we would typically use, that's your hint that this is going to be a state change, because we're going from a liquid to a gas. That is AKA vaporization. So what I'm doing here is I'm vaporizing this. I'm also not provided with two different temperatures here. It just tells me it's 100 degrees at steam. Well, I know if I look at a heating curve for water, that vaporization process is going to occur while the water is 100 degrees. So it's going to stay the same. When we did the lab on heating and cooling curves, we know that during a state change, the temperature is going to stay pretty stagnant. So that's how I know that I'm going to be using this equation instead, the phase change equation, because I don't have two different temperatures where it would be changing. It's staying at 100 degrees, but it's changing from a liquid to a gas. So my mass is going to be that 10.8 grams. And then what I have to do is look up here at these different delta H values. So I just need to choose the one that reflects the state change I'm seeing. So at this portion of the graph, I am vaporizing. So what that means is I want to use the heat of vaporization, which is 539 cals per gram. So what we find this is equal to is 5,821.2 calories. So in correct significant figures, that would be 5,820 calories. So again, my hint here is when I read through this problem, I saw that I only had one temperature and I had that keyword turn. So that's kind of my idea that I'm going to be working with a phase change. If we look at the next one, calculate the amount of heat that must be released in order to decrease the temperature of 100 grams of water from 118 to 101. So I can see here that gives me a hint that it's a temperature change. But what I want to do is still draw my heating or draw my cooling curve. I have a cooling curve now. I want to draw it to make sure that I'm not going to be undergoing any state changes. So I'm not going to be turning that 100 grams of steam into liquid or solid water. So if we draw our cooling curve really quickly, we know that the freezing point is 0 degrees. We know the condensation point is 100 degrees. So what that means is I'm somewhere in this region. I haven't quite hit the temperature where I'm going to be condensing that liquid into, or condensing that gas into a liquid, but instead stopping right before it. So that tells me that I should use the equation that reflects a temperature change, okay? And I also need to decide what specific heat to use. So my mass is 100 grams, easy. My change in temperature, remember it's final minus initial. So our final temperature is 101, our initial was 118. So I don't really like the way that looks. 118. So that means we've lost 17 degrees. Is it okay to have negative temperature? Yes, because the temperature went down, so we would expect it to be negative. And then the C value we want to use, we have to look at what state of matter we're in. So up here at the top, this is a gas, this is a liquid, and this is a solid. Because I'm working in that blue highlighted portion of the graph, which is a gas, what that means is I want to use the specific heat of steam because that's gaseous water. So 0.48 cals per gram degrees Celsius. So I'm going to plug in all my numbers to solve this. So we have 100 grams times delta T, which was negative 17. And then I'm going to multiply it by 0.48, which again is the specific heat of steam. I'm using that one because the temperature is hot enough that I'm working with steam here. Multiply this together and we get negative 816 calories. So in correct sig figs, this would be negative 816.0 cals. Okay, so these have all been relatively easy up until now because they were only one step on this graph, meaning I was only moving up by temperature or over through a phase change. I wasn't doing both. We see that changing, however, in number 4. So in number 4, you're being asked to determine the amount of heat, 210 grams of ice. It's starting at negative 20 degrees Celsius. We're bringing it up to the melting point. We're turning it into water, and we're ending at 50 degrees Celsius. So I have temperature change occurring, and I have phase change occurring. I have lots of changes that are occurring here. So the easiest thing to do when you have these multi-step problems and there's a lot happening, draw the graph first. So we're heating this up, so it's going to be a heating curve, right? We know 0 degrees is here, 100 degrees is here. So I'm going to be starting at negative 20 degrees Celsius, and I'm going to be ending around 50 degrees Celsius. So what that means is I need to figure out what kind of changes are happening in all of that stuff in between, right? So if I want to look at how these temperatures are changing over time, in the initial section, I'm at negative 20 degrees Celsius, I have to bring it up to 0 degrees. That's going to be my first equation I do, bringing it from negative 20 to 0. Then I'm going to have a phase change, which is melting. So that's going to be that horizontal portion of the graph. And then finally, I'm going to be raising it from 0 degrees up to 50. So I need to break this up into 3 separate equations. One is going to be from negative 20 to 0. 2 is going to be the melting that's occurring. And then 3 is going to be the 0 degrees to 50 degrees. So this is a really good example of why it's really helpful to draw these graphs. I know you might not like enjoy the actual process of drawing it out, but it is a way to help you problem solve this, because by drawing this out, I can see those segments that I'm going to need to solve and how I'm going to break that up. If I just plug negative 20 and 50 into a temperature change problem, I'm not going to get the right amount of calories and I'm going to get the problem wrong. So for the first one, we have a temperature change. So our equation is m times delta T times C. My delta T here is going to be 20, and my delta T at the bottom here is going to be 50. So our mass is 210 grams times 20. And if we look at where I'm at in this first portion of the graph, this is ice, so that's going to be solid, right? So I want to use the specific heat that coordinates with the solid or ice. So that's going to be 0.5 cals per gram degrees Celsius. So I multiply all that together, and my first chunk, that first segment of the graph that I'm going to be traveling up, is going to require 2,100 calories. So then I need to do the next portion, the melting that's occurring. So that's segment number 2. Because that's a phase change, it's going to be m times delta H. So the mass is still 210 grams, but I need to choose the state change that corresponds to melting, which is otherwise known as fusion. So there we go. Call it melting, fusion, whatever you want to call it. So that's going to be times 80. So here we require 16,800 calories to do that step. And then finally, I need to do that third segment, again, another temperature change, where the temperature is going to be rising up 50 degrees. And now the specific heat, I don't necessarily want to use that 0.50 that I used up here, because now I'm in a different part of the graph. Now I'm in the liquid portion of the graph for segment 3. So what that means is I want to use the specific heat of water, which is 1.0, so solid water, or liquid water. This is equal to 10,500 calories. So altogether, our Q total is going to be those 3 values that we found here, here, and here, added together to our Q total, which is equal to 29,400 calories. So to summarize, what you have to do is read your problem, decide whether or not it's a temperature change or a phase change, and then break it up from there. If you have a multi-step problem, I'm telling you now, you have to draw this graph. If you do not draw this graph, you are not going to be able to problem solve this effectively, and you're going to run into a lot of issues. So I hope that this is helpful and can help you to understand how to solve these problems. We can practice these more in class before our exam, but I'm promising you there will be problems on the exam that are just like this.